Let's explore the AI-generated synthetic data feature, which is typically used for analytics and machine learning model training. Here's how it works. You start by dragging the table you want to synthesize under the Synthesize section. Once you've done that, you let the AI do the work. All the columns will be automatically fed into our generative AI model, which preserves the relationships and patterns in the dataset and regenerates them in a synthetic dataset. If you go to the column settings, you'll see that AI-powered generation is applied to all the columns. At this point, you can decide if you want to change the number of rows. You can increase this number if needed and set the number of rows the platform will generate. Once you're happy with your settings, you can proceed to generate the synthetic data. You'll be taken to the job summary page, where you can see which tables are being synthesized and which are excluded. Finally, you can start the generation process by selecting the Start Generation button. With synthesization, you are able to generate more rows than you originally had as input. This can be useful for machine learning model training, where there might be relatively few observations of certain features or columns in your dataset. If particular groups of people are underrepresented, you can generate more output data to ensure these minority groups are better represented and boost the performance across your entire dataset. To do this, simply change the number of rows to generate. For example, you can set this to 1 million. The trained generative model will then produce and write 1 million rows into your output database rather than the original number of rows. This upsampling combined with AI-powered generation can significantly improve your analytics and machine learning model performance. Let's explore how AI-generated synthetic data works for time series or longitudinal data. In this example, we have a time series dataset for baseball players consisting of a players table and a seasons table. The players table contains information about the players, while the seasons table contains the sequence or time series information. For each player, we have multiple observations across different seasons. To preserve this sequential information, we developed a sequence model. To use this model, you can select the Generate option and enable sequence modeling by pressing this button. Once enabled, you can start the generation process and wait for the sequence model to complete the data generation. So how does the synthetic data that we generate look like? Let's have a look at the original data that we used as input for the synthetic data generation. Here we have the original patients table, where we see a variety of their corresponding information. Now let's examine the synthetic version of this table that we just generated. You can see that the synthetic data looks very similar to the original data. However, it is completely newly generated using our generative AI models. If we compare the two, you'll notice that the rows are entirely artificially generated. Despite this, the relationships, patterns, and properties of the original data are still reproduced in the synthetic set. For example, if we look at the birth and death date, you can see that the death date is always later than the birth date. These are typical relationships that are preserved in synthetic data. More complex relationships, such as the correlation between latitude and longitude or between location and healthcare expenses, are also maintained. In some locations, healthcare expenses might be higher, while in others, they might be lower. These patterns are all preserved in the synthetic data. This is the essence of AI-generated synthetic data. You let the generative AI do the work to create entirely new synthetic data that still looks and feels like the original data. Now let's take a look at our quality assurance report, where we compare the original and the synthetic data in terms of data quality and privacy. First, we have the privacy metrics, comparing 3 different metrics between the original and synthetic data. The first metric is the identical match ratio, which looks at identical matches in the synthetic data relative to the original data. The next metric is the distance to closest record ratio, which considers not only identical matches, but also near matches from the synthetic data to the original data. Finally, we examine the nearest neighbor distance ratio, focusing specifically on outliers to ensure they are not reproduced in the synthetic data. Next, we move to the univariate distributions, comparing the original and synthetic data column by column. For example, if we zoom in on the gender column, we can see that the original data has a roughly 50% female-to-male ratio, and in the synthetic data, it's virtually the same. We can also explore other columns, including numerical columns and date-time columns, which are visualized as line graphs. These graphs show how well the original and synthetic data overlap, indicating that the synthetic data accurately reproduces the patterns of the original data. To go more in depth, we analyze correlations between specific variable combinations. For instance, when comparing the original and synthetic data, the correlation between variables such as county and city remains strong in both datasets, which is exactly what we aim to achieve. These results are consistent across various industries, including healthcare and finance. The metrics are industry agnostic, demonstrating that your synthetic data remains valid and can be effectively used for your use cases regardless of the sector you operate in. Let's look at some of the evaluation results from the experts at SAS on our synthetic data. How did they do this? In a project aimed at predicting customer churn in a telco company, they used a target dataset of 56,000 customers with 128 different columns to predict whether customers would churn or not. They trained 4 different types of prediction models and evaluated how well the original data performed on those models, how well anonymized data performed, and how well synthetic data performed. In the results, we see that the original data always produced the best results. However, the anonymized data had significantly inferior results, with an area under the curve value close to 0.5, indicating that the model was predicting at random, so it did not perform well. On the other hand, the synthetic data's performance was nearly identical to the original data. These are the main findings. Synthetic data performs almost as well as the original data, while anonymized data shows the worst performance. Another benefit of synthetic data is that it is easy, fast, and scalable, which is a significant advantage over data anonymization. If you have any questions or anything you would like to share, feel free to reach out to us via our website or schedule a live demo with us. Thank you for watching.